Okay, I open it. Yeah, I thought there was a problem with the room. That's why. Okay, I just opened it. I will close this.
Like,
Okay.
check if they can hear you now.
Okay.
But I don't know.
Now it's better. Okay. Okay, now I think it's okay. Yeah? Let's see. Okay, they can hear now. So here we see that if you take an adjacency matrix and we take the to the power of 2, then we got the paths that connect two nodes of length 2. And if we want the paths of length 3, we just take the cube of this matrix. Here there is an example of how you can compute the paths of size of length 2. Okay, also we have already talked about directed and undirected graphs. The adjacency matrix is not symmetric in directed graphs. An important thing to know is the nodes degree. How many are the adjacent nodes in the target node? Okay, here we see that the target node V1 has, let's say, 9 adjacent nodes. So the node degree is 9. We see here how also there is an important thing is the outgoing links and the ingoing links in graphs. Okay, so how many are the outgoing links from a target node? This is the out degree. The in degree is the number of incoming links in the target node. Okay, here we see how you can compute it. The weights, also a very important thing in graphs is the weights that we put on the edges in order to express, let's say, similarity or distance between the nodes of the graph. Here we see the airports in USA, and we can see the distances of the airports. Of course, we use these weights in order to run our algorithms. We will see a lot of many algorithms about random walks. Let's say the random walk with restart, personalized page rank. All these use walks, which is the sequence of incident edges visited one after another. So this walk here we can see an example. A walk of length 8. So these are the number of edges that are crossed, are traversed. So a path, what is a path? A walk, it is a walk where nodes and edges are distinct. Okay, so this is a path. The nodes and the edges are distinct. So you visit them just once. This is the distinct. And when we have a closed path, then this is denoted as cycle. Okay, so when you visit a second time a node, then this is a cycle. This is a closed path. And of course, these closed paths may create some problems to the algorithms because the random walker will, let's say, will be trapped in during its traversal to the graph. Okay, so we need to find some ways to give an exit to this trapped random walker. Okay. So here we can see a path of length 4. The number of edges that it traverses. Okay. So these are also called hops. Okay, the hops. So if you have yeah. Okay. So one important property that we have to keep in mind is the fact that the random walker should the probability of visiting an outgoing link should be equal to the sum of probabilities of using one outgoing link being in a target node should be equal to 1. Okay. So this is a very important property that we need to keep in mind. Of course, we will use graphs for recommender systems. So this is an important thing, how we can use the graphs in order to provide recommendations for businesses. Already, it's a big industry. All the companies, big companies and sponsors of this conference are using recommender systems. And there are many issues to be solved. So we have to focus on providing recommendations which are in the long tail of the item popularity. So we should focus on the large number of products with low volume. So this is something that we have to focus because it can satisfy the preferences of the users. And of course, the problem, usually in recommender systems, we use a user item rating matrix to present the initial problem, but this user item rating matrix can be easily represented also with a bipartite graph. Okay, we see here a bipartite graph. On the left side of the graph, we have the users. On the right side of the graph, we have the movies. And in the bipartite graph, there are only connections between these two entities. Okay, so we have two different entities in this bipartite graph. And also, we could have other type of graphs like this heterogeneous graph, which does not have only the user item rating interactions, but also it has the connections of friendship that connect the users of a social network, let's say, in this example. We can have even higher order graphs like tripartite graphs. And here we can see an example of users who visit some point of interest and assign some kind of photographs or videos for this tag, some kind of information objects. Okay. About similarity, very important issue is how you can infer similarity in graphs. Okay, so of course, we have to keep in mind that how similar are, let's say, here node A and node B. In order to infer this, you need to take under consideration many things. For example, how many paths are connecting these two nodes, or if there is how this the weight of the edges also is very important. Okay, of course, if the paths that connect the two nodes are short, this may be considered as a high indication of closeness, of affinity, okay, of relevance between the two nodes. So the number of connections, how many are the paths that connect these two nodes? Okay, paths of size 2, of length 2, paths of length 3, etc. The weight of the weights of the edges also can be considered. And of course, when we try to solve these problems with graphs, what we want to predict is the links that will occur in future. Okay, so this is the thing that we want to predict. If there will be, let's say, a connection link between a user and an item. Okay, so this connection link could be a purchase of an item from the user. So we have the time also is very important. We need to take time-oriented snapshots of the graph, and then we try to predict the new emerging graph edges in the graph, of course. So there is like the time is very important to manage this kind of graph structures. Also, as far as the similarity inference it concerns, there is also the two different families of computing of inferring relevance in graphs. The first is node dependent, when you use the nodes and compute similarities between the nodes that are adjacent or in close distance. Okay, here we see the common neighbors. This is like the algorithm that is used in Facebook. Okay, so when they provide the you are suggested a friend because you have common friends with him. Okay, so this is the way. So this is the first one. The friend of a friend suggesting. Also, there are other measures like Adamic Adar. There is the Jacquard coefficients, which is the number of common neighbors divided in the denominator to the union of the nodes neighbors. Also, there is preferential attachment. The rich gets richer. Okay, if you have many adjacent nodes, you will probably be connected in future with other nodes more easily. Okay, so here is the product of the number of adjacent nodes between the two target nodes. Okay, Vx and Vy. These are the two target nodes, and you can predict that these two nodes will be connected in future because of the high number of adjacent nodes that they have already. So if they are, let's say, top scientists, it is more easily for them to be connected because of their common, let's say, papers, etc. However, there are also global metrics for computing for inferring similarity in graphs, like the CATS status index. Okay, as you can see here, there is this vita. This is an attenuation factor, which attenuates the weight of the importance that you put on path, if this path is of size L. Okay, so if you have paths that are of higher size, then you should attenuate their importance. You should put more importance to paths that are smaller, okay, of size 2, let's say, not of size 10. Also, we have here the computation of random walk with restart. We have the identity matrix here, the transition probability matrix, this is like the modification of the PageRank algorithm in order to use it for similarity inference. You can hear it also some personalized PageRank. Also, SimRank is important. This is like a random walk also based algorithm, which considers the fact that there is if the people that cites us are similar, then we are also becoming similar. Okay. So all these algorithms can be used in order to use this similarity inference. Now I will just give a detailed presentation of the random walk with restart algorithm, which is based on the PageRank. Of course, you all know the PageRank algorithm and how it provides importance to pages, the websites. There is the random walker model. This random walker starts its journey, and we want to compute the probability of find him after his journey in a node of the graph at page. Okay. So an important data structure that we should use in order to compute the PageRank of a graph, of the nodes of the graph, is the transition probability matrix. Okay, the transition probability matrix, in essence, is the product of the adjacency matrix times the inverse of the degree matrix. Okay, so keep this in mind. So here, an important property of this transition probability matrix, so that we can run the random walk with restart and other algorithm, is the stochasticity. Okay, so this means that the values of the rows of each row should sum up at 1 to 1. Okay. In our slides, the columns will sum up at 1. Okay. So it depends on the authors how they define this stochasticity. Okay. So this means that the outgoing links of or the incoming links, the weights of the incoming links in the target node should sum up to 1. Here we see an example of a graph, a simple graph, which consists of three, let's say, nodes, Yahoo, Amazon, and Microsoft. And we take under consideration the incoming links to infer the importance of these nodes. Okay, the incoming links. Okay, so for example, here, in order to infer the importance of this node, we take under consideration the incoming links, which is this y divided with 2 and a divided with 2, since Amazon and Yahoo have 2 outgoing links. Okay. For the Microsoft, for the Amazon, you can see there is the incoming link that comes from Yahoo and the Microsoft's link. Okay, so this is how we infer the importance. In this case, since we have a simple example, we can solve it easily. So here is the column vector of the 3 web pages, Yahoo, Amazon, and Microsoft. Here is the transition probability matrix. And as you can see here, it is column-wise. As you can see here, the sum of the values per column sum up to 1. Okay. So, of course, these systems, linear systems, have many solutions. In order to acquire one unique solution, then we should enforce a constraint. And here is the constraint. So the importance of Yahoo, Amazon, and Microsoft should be equal to 1. The sum of importances of these 3 web pages should be equal to 1, and then we can have a unique solution. Okay, so the importance of Yahoo is 2 divided with 5, of Amazon 2 divided with 5, and of Microsoft 1 divided with 5. Of course, for a simple graph, it is easily to compute, but for large graphs, this should the method that we use is the power iteration. Okay, so we needed to use this random walker and make a subsampling of the computations in order to have a fast solution and fast convergence. So here is a description of the power iteration procedure. We need the initial vector of the graph that expresses the importance of the nodes of the graph. Here is V. V, the value should be, let's say, equal to 1 as an initial vector. Okay, or it could be like 1 divided to the number of nodes of the graph. Okay, if we have 3 nodes, then every component of this vector should be 0.33. Okay, so you need the initial vector that keep the importances, and then you need also the transition probability matrix. And you start to make multiplication between these 2 structures. So this is the initial vector. We usually start with 1, or we use this 1 divided with n. And then also, here we can see how we can compute the importances of the nodes. We start with the transition probability matrix times the vector, the initial vector, and then we compute the v prime. And also, in the end, after several multiplication, we result to the importance of the nodes of the graph. Okay, Yahoo and Amazon have higher importance in terms of importance than Microsoft, which is easily explained since Microsoft here has only 1 incoming link, whereas the other 2 have two incoming links, which means that they have a higher importance. Okay, this is an intuition that we can get. Of course, there are problems that exist in real-life graphs, like dead ends. Here we see an example of a dead end. Or spider traps, where the random walker cannot escape from a node. In the node C, this is a net dead end. So the random walker cannot continue its journey. Whereas if there is an outgoing link, in this case, in the second graph, this is a spider trap, which means that this node will accumulate all the importance of the graph during this multiplication of the transition probability matrix with a vector of the importances V. Okay, and here we see the formula, the equation that we use for computing the random walker with restart. So here is the V prime, which computes the similarities. Sorry, here we talk about the page rank, so this is for the importance. So here we have the V prime. This is the M, the transition probability matrix. Here is the V, the initial V. And also, in order to solve the dead link problem and the spider trap, we have a teleportation, let's say, trick, which is the Vita is the probability of a node. Vita is the probability of the random walker to continue to its journey to the outgoing links, whereas 1 minus Vita is the probability of the random walker to jump to any other node of the graph. Okay, so and this is in the end we have this vector, which is a vector where its components is one divided with n, which is the number of the nodes. So the random walker has an equal probability to jump in any node of the graph with equal probability. Okay. The different names of the page rank in terms of the node similarity: personalized page rank, random walk restart, rooted page rank. And here we see how this is a visualization and animation of how the nodes that are close to the initial node in this random walk restart algorithm become more important in terms of relevance to the initial node. So here the node 4 is the starting node, and as you can see, the random walker starts its traversal and returns. So yeah, and now we have the computations. The most relevant nodes of the target node 4 can be considered. This is the node 1, node 3, node 5. So these are the adjacent nodes. They become red. They are the adjacent nodes. But also you can see that the nodes 6, 7, and 8, which are not adjacent nodes, have more relevance than the other nodes of the graph. And if you in graphs, they usually use these random walks. We have node to vec algorithms. There is a deep walk algorithm. There is a family of algorithms that use the random walk restart. Okay, so as a first notebook Jupyter here, there is an example that we should see about these random walks, and it comes from the book, and it has to do in a heterogeneous graph. We see here there's a graph that consists of 4 different types of nodes. We have the persons, the users, we have the sessions. So this is a node that captures the information of the time information of a fact. We have also the articles, and also we have the categories of the articles. Okay. So if we go now to the code, this is the example 8.5 from the tutorial, and I guess we can go together now to have a look at it. So if we return to the web page, here, we can go in this book example 8.5, if I'm not wrong. Yeah. And now we are in the Colab environment, where we can see, in order to use this, to run algorithms in graphs, we can use this NetworkX library. This is a nice library that helps us to work with graph structures. There are many things that are already implemented, and we can use it. So the first thing that we need is to add the nodes of the graph. And as you can see here, we put Anne, Mike, the persons. Here we have the sessions. We have the articles. And for every different entity of this graph, we create a different type of node. Okay. Then we put the edges that connect the different nodes. Okay, a session with an article with the articles category, and also, yeah, we can visualize the graph easily with this command draw NetworkX. We start, as you can see, with the initial matrix, the adjacency matrix, and then we can compute the degree matrix. Okay, so we have the calculation of the degree matrix in order, in the end, to take the product of the adjacency matrix to the inverse of the degree matrix. Okay, so the product of the adjacency matrix to the inverse of the degree matrix gives us the matrix M, which is the transition probability matrix. This matrix M is the transition probability matrix, which will be used in our equation. Okay. So here you see we start with the parameters of our equation. Beta is the jumping factor, and in this case, the jumping factor to the initial starting node. So it's 0.8 that it continues regularly its journey to traverse the graph, and 0.2 to return to the starting node. Okay. And as you can see here, the algorithm is just one line of code. Okay. This is like this. This is the PageRank algorithm and also the random walk restart algorithm. And it's in terms of a linear algebra matrices, it's just one line of code. The beta parameter, the transition probability matrix, the V initial vector, and the identity matrix. Okay, and of course, this easily converges after some steps. And yeah, in the end, we have the relevances, but of course, these relevances cannot be considered as a similarity measure because they are not symmetric. Okay, you use this methodology, but you use them to compute a relevance and not a similarity metric. Okay, it's not like the cosine similarity, it's relevance here. And in the end, as you can see, you can have, by using these random walks, you can have an extended matrix with the persons, with the sessions, the articles, politics, and you can infer relevance of a person with a specific category, articles category. Okay. So this was, let's say, the example. And of course, we could find also this to the book. So if we go to the book and go to chapter 8, there is this chapter is devoted to graphs. Okay, so there are about what we discussed about global-based metrics and the CAT status index, the SIMRank algorithm, okay, the definitions, and the example here, exams with the articles. And also we have a bipartite graph here with the computations of the bipartite graph. We have here the random walk with restart equation. And here is the example that we just did. And there is, let's say, some, and here you can see the relevance of these two users, the Anne and Mike, with politics and economics, but also we can have at the same time the similarities between articles. So here, this submatrix, we can see the similarities between articles with articles. And yeah, we can have also algorithms like PathSim, which runs on metapaths. We will see later some state-of-the-art algorithms on this category. And yeah, in the end, there is also the knowledge graphs here, graph convolution networks, an example that we will see later. Yeah, and in the end of this chapter, there is the code. Yeah, you can see the code that we just saw. This is with some findings. For example, although Mike has read a politics article and an economics article, we can observe that their scores are not the same because the politics article appeared in the same session as the economics article. So there are some discussion about the findings of this algorithm that we just present. Okay, so this was the first part, and now we continue with graph neural nets. This is like the material from chapter 6 of the book. And of course, now we are in a state that we want to represent everything with neural nets. And the building block of the neural nets is the perceptron. Let's see in fast the architecture. So the perceptron consists, this is the architecture of a single layer perceptron. We have the input vector. We have this input vector X. So we have the weight vector, the vector of weights. And then we have some computations like the weighted sum, activation function. Okay, so this is the main structure of a perceptron. The weights are located on the directed edges. So this is like a graph also, but okay, it can be considered as a tree. Let's say there are no cycles usually. This is if it is an MLP, let's say. The weights located on the directed edges connecting a neuron of one layer to the neuron of the next layer. So this is when we use graphs, what we want to, or neural networks, what we want to learn is the weights of these edges. Okay, so when we say I want to learn a neural network, so usually what we train is the weights of this network. Okay. Of course, there is also the bias. It's additional node to the input layer with fixed value. The bias node also ensures that the output of the neuron will not always be the same, so that we have a non-deterministic, let's say, operation of the perceptron. So it means that we will not result always in the same result. That's what we try to make happen. Of course, by having the x, which is the input vector, and the weights, which is the w, the weights vector, then we make some computations, and this is the weighted sum. Okay, this big sigma here, this big sum, it's the weighted sum, which is this equation. So x, the input vector, times the weighted vector, the transpose of the weighted vector. The weight vector is the vector that keeps the weights of every link of the input layer and the perceptron. And we have also the bias. Okay, so this is the weighted sum. And after this, we have the activation function. So the last part of the operation of a perceptron is the activation function. It uses as input the output of the weighted sum. Activation functions are divided into linear and non-linear. Choosing an appropriate activation function F is a critical part of neural network. So the activation functions, we have the linear or identity activation function. So regardless of the number of layers of the neural network, its next layer will be a linear function of the previous layer. The sigmoid function, ideal as the range of probabilities also in the 0-1 values interval. So this is in the 0-1 values interval for the sigmoid. And this is the equation. The hyperbolic tangent activation function. This is the equation, and its values range from -1 to 1. This produces a zero-centered output. And here we can see the diagrams of activation functions. Of course, we have also ReLU, which takes the max from the input between 0 and z, which is the input, and leaky ReLU also with some attenuation factor before. And of course, these activation functions have some problems and some advantages. Here we can see some advantages of the sigmoid. The fact that it outputs in a bounded range. So the values that it outputs is in a bounded range. However, it has the vanishing gradient problem. Okay, so this makes the algorithm to moves around the zero. Okay, so it cannot converge easily by having this problem of the vanishing gradient. Hyperbolic tangent also, the advantage is that it is zero-centered output. However, it's also have the problem of vanishing gradient. And of course, this means that it saturates as we move away from zero. and it is computationally expensive. We have the ReLU. This ReLU avoids vanishing gradient, so it solves the previous problem, but however, it has the problem of exploding gradient. Okay, so as you can see, there are pros and cons in using these activation functions, and also the leaky ReLU. So another important, of course, there is also the softmax, which is a way to compute some kind of probabilities. So in the nominator, we have the one, let's say, link that goes to the perceptron, and in the weight of one link that goes to this perceptron. And in the denominator, we have the sum of the weights of the links that go to the perceptron. And in this case, we can compute, this is a kind of an attenuation factor for us. We can see which is the one that it is the most important. Okay. So this softmax is used a lot in neural nets, as you may know already. And the good thing, it is probabilistic, and this means again that the output, the sum of the outputs sum up to 1. The end of the neural nets have always loss functions. Okay, in order to optimize your neural net, in the end, you need a way to measure how far you are from the ground truth. How different is your predicted rating to the real rating. Okay, that's why in the end of the neural nets, we use one loss function. And here we will see two different kinds of loss functions. The one is the regression loss function. It has to do with the ratings, the rating predictions. And here we can see that we use the squared loss between the real and the predicted rating. Okay, so if we have an input of real ratings for users, so this is the real rating for user X1, this is the real rating for user X2, etc. And we make some predictions with our neural net. So this is the y hat is the predicted rating for the user X1. The y hat 2 is the predicted rating for X2, etc. Then we can take the square loss of the difference between the real and the predicted ratings, and we can compute the MSE, okay, the mean squared loss. Or the RMSE, or whatever you want to compute, and you can use it as a loss function. This is the regression loss function, and of course there is cases that we want to use other types of loss functions, like classification loss functions, where we have again two different types. Here we have a multi-class classification problem with the class 1, class 2, class 3. Class could be a color red, color green, color yellow, anything. So in this case, you have the actual colors. So this is the color, the true color for the items, let's say. And also in your neural net, you will make some predictions. So the red color is the output. So these are the Q. Are the outputs of my neural net. So this Q1, Q2, Q3 are the colors that we predict. And in this case, we can use, and what we want to predict is that we want, if a ball is red, I want to predict it red. If a ball is yellow, I want to predict it yellow. And in this case, we use this cross entropy loss objective function in order to compute how far is my predicted Q value from the real P value. Okay, and we take the sum and we compute this quantity. Of course, if we have two classes and we don't have many classes, like in our example, we can compute the binary cross-entropy loss, okay, which in the end results in this equation, which should have seen in many papers, because all the papers with neural nets use this specific objective function in the end. Most of them, let's say 9 out of 10 papers, this is the binary cross-entropy loss equation. Again, so the y is the real, let's say the y means that this item is recommended in reality to the user, and the y hat, this one, is what we make as prediction if we will recommend it or not in our recommendations, okay, of our neural net. And by having this quantity, the log of these quantities, we can compute the binary cross-entropy loss. So now we are going more to neural nets. We start with convolution neural network, which is, let's say, the reason why everything in the next 10 years, in the last 10 years, have moved to neural nets. So all algorithms right now are neural nets. Everything are neural nets. And this is the reason that they became, because in image processing, they used convolution neural networks. Okay. And they have so high effectiveness in their predictions, who convince everyone to use, like now, a neural network. Okay, so in this case, the convolution neural networks consist of two main layers: the convolve layer and the subsibling or pooling layer. Okay, so the convolve layer, it is responsible for the creation of two-dimensional feature maps. Okay, so, and we can see it here. So we have an image and we extract specific, let's say, graph, let's say objects, and create some feature maps. Okay, so this is the convolve stage. As you can see, we extract some features from the initial image and we create some feature maps. This is convolution stage. And then the second is the subsibling or pooling layer, where we reduce the feature maps resolution. Okay, so we have these feature maps, and for every of these feature map, we just make it, we create a subsibling of this feature map. Okay. And of course, there are different ways of subsibling, like to aggregate this information, get the highest value, or make an average of the values of, etc. And after this, we can see here there is a fully connected layers. And in the end, there is a softmax here, loss function, which is able to compute if this is a bird, or if this is a sunset, or if this is a dog. Okay, so there are, let's say, convolution neural networks right now, like ResNet, etc., which highly used in such kind of predictions. Okay, so this the revolution in convolution neural network help in order to have also a lot in natural language processing right now with chatbots and all this ChatGPT and everything right now, which is like a very, very important development. So, but here also we have the graph convolution networks here. We in order to run a graph convolution network, we again need an adjacency matrix, and also we have to keep in mind that in the nodes of a graph, they keep some features. So we should always keep in mind that the nodes they have some node features like name, title, role, everything. I don't know if it is a protein, it has other features, but everything in a graph, it has node features. And this is what we want to understand. So can I predict the features of a node by using the features of the adjacent nodes or of the neighborhood of the nodes? Can I express a node, or can I predict the features of the node by using the neighborhood of this node? And this is how this graph convolution network works, okay, in essence. Okay, so we will start now with the graph neural networks. We have 10 more minutes to have our break, so I will continue in this space. And we will make our break. So here we see how this graph neural network is. So we take the raw data. From the raw data, we create, let's say, the nodes. Let's say that these nodes are persons and they have some attributes. And now what we want with the graph neural nets is that can I represent a node with his features in a more compact way? And this is the embedding. When we hear node embedding, this is it. Okay, so it's a compact representation of a node. Or a node can be a person, can be a protein, can be everything. But when we talk about node embeddings, it's like a visual representation of the node in a more compact way. And this is why we use this vector here. So these are vectors, of course. And in the end, you want also the optimization procedure, and you should have always, as we said, the loss function, which can be a pointwise or pairwise loss function, etc. Okay, so this is the GNN model in general. Of course, the GNN models can be combined can be divided into two big categories: the spectral models, which use the graphs are transformed into signals, and this means that they are inserted in a spectral domain by using the Fourier transform. And in this case, the spectral domain refers to the representation of data in terms of frequency and not in terms of time or space. So we have a transformation of the initial graph to represent it as signal. So we have a, let's say, patient, and we take the ECG. The ECG has some volts, and we have some the time dimension, and we take this information and we transform it in the spectral domain. So in the end, we are interested only for the frequency of the signal in order to have the ECG signal and check the condition of the heart of the patient. Okay, so this is the transformation we do. And the second that we will use mostly in this tutorial is the spatial models, where we conduct them on graph structures and we extract localized features and we use the weighted aggregation in order to express one node with the nodes of the adjacent nodes of the graph. Of course, the way that this information propagates may be different, and there are different methodologies that can be used in order to make this feature propagation happen. As we said before, what we want is that we want to express one node with the characteristics of the adjacent nodes or of nodes that are in the neighborhood, let's say 3 hops in distance, 3 hops. Okay, so imagine in the center of the target node, and we have concentric cycles, and we want to go 3 hops far and bring and propagate information to the target node and predict the node characteristics and create an embedding for this node. And we have different, let's say, methodologies. One which is used is GATT, which is like a whole family of mechanisms that utilize the attention mechanism, okay, to aggregate network features. Also, the RecSys can be used. And as you can see here in this, let's say, visualization, the idea is that how you will propagate information from the other nodes to the features of the target node. Okay. So how you will make this aggregation, or how you will consider one node as more important. So should I trust all the doctors equally, or should I put some more importance to a medical doctor who has made 2,000 operations and they all lived after the operation? Okay, so this is the idea of the GATT. Not all adjacent nodes should be considered as equally important, but I should put more importance to those that have, let's say, attracted the attention of the user more. So if I want to build a user model and predict the user preferences, he was during a session and he stayed in one item and then in another item and then in the third. Okay, but in the second he stayed 2 minutes. Okay, so if he stayed 2 minutes and in the third he skipped it, I should put more attention to the second item and bring this information to my neural net. This is the idea of how this attention mechanism works. Okay, and we will see many now state-of-the-art methods, mostly in the second after the break, about these developments. For example, I can just I can stop here, and maybe we will continue seeing more detailed information about the algorithms that, as you can see here, there are some equations, and we will see in detailed parameters of these equations and some papers about the GATT, the graph attention networks, and there are some methods that have been used, like, but I just show you to have an idea of what we will discuss after the break. I don't know if there is any question now. For the last 3 minutes, I would be happy to answer. Okay, so now we are in the middle of this tutorial, and yeah, this is I mostly talked about the preliminaries in graphs, and I am about to start with state-of-the-art algorithms in the field of recommender systems, which have used graph neural networks to make predictions. Okay. So, see you after the break. If there is anyone who is interested to make any question, I will be here for 10 minutes. And also I would be, for those that have the books, if you can bring it back, it would be good. Okay, so see you later. Okay, so let's begin with the second session of this tutorial. For those who have just arrived, this is a tutorial in deep recommendation using graphs. This tutorial is based on 2 chapters from my book, Deep Recommender Systems with Python. I have 2 sample copies here for those who want to see them in more detail. Now we will see some works in graph convolution networks. The first work is about Yu et al. In its Sky 2019, and it has to do with recommendations using social relations and mobility data. Okay. So as you can see here, we have a bipartite graph, an heterogeneous graph, which consists of entities such as users who visit a certain point of interest. And we have also interactions between users. So we have information about meeting frequency or visiting frequency and co-occurrence of co-visit in point of interest, etc. So in this case, this method used the convolution neural network in order to propagate the information to the target node. In this visualization, this is the red node. So this is the target node. And what we want to do is to make predictions about this vector. Okay, the vector of the target node. And as you can see here, somehow we need to propagate the information that comes from different type of nodes. So we have the orange nodes, which, as we can see here, are point of interests. And also we have the blue nodes, which are the users. And we have different arrows. As you can see here, we have the purple, the green, and the yellow. So this means that there are different type of interactions between users or point of interests. So the purple link is about user-user interaction. So it should be like a friendship. The green is user location interaction. The yellow is location, the co-frequency, the co-visit of certain points of interest, etc. So if you go to Bari and you visit 3 points of interest, then there is a kind of relevance in this point of interest because of the distance, probably, or because of this sequence, etc. Okay. So as you can see here, we have the map. We have four users. Every user has a different itinerary, plan of visits in the city. Let's say it's Bari. And okay, this method uses this information in order to create a graph. And and based on this graph to propagate the information and express one node with the help of other type of nodes or adjacent nodes or nodes that are in the neighborhood. As you can see here, the convolution layers are two. So the first convolution layer is this. The second convolution layer is the nodes which are in 2 hops distance. Okay. And they use a recurrent neural network. And probably this recurrent neural network is used in order to forget, let's say, information which is time obsolete, let's say. Okay, so this is the idea. So the recent events should be considered as more important than events that happened 2 years before. Okay, it's about visiting things, point of interest. You should have some kind of recency in the events. Okay. Okay, so here you see that this is the loss function. It consists of 3 parts, 3 terms. You have here FU and phi U and phi V and phi W. So U is the target node, and also there are nodes which are not homogeneous. So then V is also a user node, and also there is the W. So there are different type of nodes in this case. And also there is the negative sampling. What do we say with negative sampling? Negative sampling means that we should not train our neural net only with positive interactions, that the user visited a specific point of interest, but we should also put and feed the neural network with negative interactions, which means that things that did not happen at all. So those randomly selected user location interactions or user-user friendship connections that are do not exist in reality, but we have to put them there in order to have a balanced way of training our neural net. Okay, so this is why we have this negative sampling in this method. Okay. So this is the main things in this slide. Of course, here you can see the main equation, which is used in almost all papers that are using a graph convolution network. Okay, so here you can see this is the H. The H is the node and the features of the node, the target node. Okay, so H is the variable that represents the node, the target node, and the features of the node. Okay. W is the weighted matrix, as we said. W is the weighted matrix, the weights that our neural net should learn. Okay. You have also here the neighborhood of the target node on the type of edge R. Okay, so since we have an heterogeneous graph, we have different type of edges. Okay, and here this first big sum represents the different type of edges. Okay, so we want to express our target node, the features of our target node, with information that comes from different edges types. As we saw before, it was yellow link, purple link, etc. So every different link brings semantically for us a type of information, and this is why we have this, the first big sum. And then for every node that belongs in the neighborhood of the target node, considering this R link, type of link, we make these computations. So we from every layer of one convolution layer, we bring information to the next convolution layer. Okay, that's why we have this lambda L parameter here. Okay, because this represents the layer which is we want to convolve the information. So from layer L, we want to convolve it to layer L plus 1. Okay, so from one layer to the next layer. Okay, so like this here, this is the target node. From this layer, which is the third layer, we want to bring the information to the second layer and then to the third layer. Okay, this is how it works, from one layer to the next layer. Okay, and so I think these are the main, and here we have a constant, this C parameter. This is a kind of attenuation factor based on the size of the distance of the target node to the node that we are considering. Okay, the same equation. This is the equation formula for the graph convolution neural networks. And we can express it also with the help of linear algebra matrices. As you can see here, this big equation consists of 3 terms. And this product, the inverse of the degree times the adjacency matrix times the inverse of the degree is the transition probability matrix that we discussed earlier. It's the Laplacian matrix, sorry. And we have also different type of information that comes from the user-user graph, from the location graph, and from the user location graph. So we have 3 different types of information that we want to incorporate into our model. So here we have 3 different terms, and every term brings information for the target node from different subgraph. The first is the user-user subgraph, user-user. The second term is about location, and the third term, this one, it's about user location. Okay, so this is in essence the method. This is the loss function, and in the end, they had some experiments with 3 different data sets: Gowalla, Bright-Kite, and Foursquare. And in terms of, I guess it should be like precision. And they developed a GCN on user mobility for social relationship. Okay. The area under ROC curve, this is the metric. Okay, so the next paper that we will discuss about graph attention networks. This work is from Velikovic et al., ICLR 2018. So in this type of networks, we said also before that it is the way that they propagate information. And in this type of networks, these GANs, we can see them as GANs or GATs. GAT. They want to, the main idea is that they want to deal with the non-regular data structures. So when you don't have always nodes with the same number of adjacent nodes, and you don't have fixed size neighborhoods, and in this case, when the data are irregular, this is a good approach to deal. So this is based on attention mechanism that you can use. And here we can see that you have a way to extract these importances of the incoming links for the target node. Okay, so as you can see here, we have the W matrix, which is the weights, and also the H vector, which keeps the features of the target node. Okay, so what we want to compute is alpha, which will indicate then the importance of node J features to node I. So node I is our target node. Okay, so for the target I, we want to find which node's features should be considered as more important. Okay, so this is the idea. Since a node has adjacent nodes, and you have incoming links from these adjacent nodes, you have to understand if there will be someone who should be given more importance than the others. And this is what happens here. And it is also used the softmax activation function. Okay, so here we have in the nominator, we have the importance of one link. And in the denominator, we have the sum of the importances of all links that are incoming to the target node. Okay, so this is the this gives us the importance of an incoming link for the target node I. Okay. If you have any question, you can feel free to make any comments, and we can discuss it. Okay. Yeah. 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 Yeah, that's why you get equal number of interactions. So if you have if your interactions, the user item interaction are 100, you should take randomly 100 negative interactions that didn't exist in the past. Yeah, okay, okay. So I would say that we can discuss this later, of course. Okay, but if you have any question about something that you don't understand, it's not about discussing something that it is extended beyond the scope of these slides. Okay, in the end, we can discuss anything you want. But let's now concentrate what we see here in this slide. Okay, we want to discuss the importance of the alpha variable and how it is computed. Okay, if there is any question about this, okay, but this is something that we can discuss later, of course. Okay, so in this GAT methods, and this method is used in many papers. If you read the bibliography, there are hundreds of papers that use this type of information propagation. One of the key things in this methodology is what they call it head attention, multi-head attention. Okay, multi-head attention. And here, as you can see, what is multi-head? So what you want is to express the features of this node H with the features of the other nodes of the adjacent nodes. So you have H2, H3, H4, H5, H6. So as you can see here, when we call it multi-attention, it means that we run 3 times this. So this says K equal to 3 heads. So we run it 3 times, and we compute 3 different weights for every link. Okay. So this is the idea of multi-head. And of course, there is also the fact that there is incoming link also to the target node itself. Okay. So this is the outgoing incoming link for it. Yeah, and here you can see you have the target node HI. This is the target node, and we want to bring information from the features of the HJ node. Okay, but also at the same time we want to bring the features of the J node, but we want to compute a kind of importance for these features. Okay, so this is this alpha that we discussed, A here. Okay, alpha is here. Okay, so they did experiments here with different data sets, Cora, CiteSeer, PubMed, that comes from the for medical publications. And they wanted to make a classification. This is the problem that they want to solve. As you can see here, they color some nodes by inferring the class of the nodes. And of course, this methodology, this CAD attention network, outperforms all other methods that come from deep learning, graph convolutions, and attention and self-attention methods. Okay, so this is something that it is really used for in graph neural networks. Okay, the GAT, information propagation. Now, we proceed with some other works in the social recommendation. We have the graph neural networks models. And of course, in these graph neural networks models, we have the information that comes from the social graph, so the friendship links, but also from the user item rating matrix. Okay, so as you can see here, this is the timeline. We have a method like the HopRec method, which is an early effort in social recommendation. It only models social networks with a GNN, the graph neural. Okay, then in 19, in the World Wide Web conference, we have the GraphRec method that we will discuss. And it models both social networks and user interactions. And later, there is also the work of DGREC, published in the Wisdom Conference, which introduce additional information to further enhance the social recommendation. Okay, so these are the 3 works that we will discuss now. As the first one, the HopRec, higher order proximity for implicit recommendation. This proposed from Young et al. In RecSys 2018. The main idea, they use a factorization model like the BPR, Bayesian personalized ranking. Okay, they use there the pairwise loss function, and also they use a graph model. Okay, so the combination of these 2 things are the HopRec. Here we see the user item interactions in a bipartite graph. Okay, the fact that a user has interacted with an item. And as you can see here, with what they perform is a k-order random walks. Okay, so from one user, if you want to move 2 hops in distance, you have to go to another item, another user, another item, actually, and another user again. So this is the 2 hop distance. 1, 2 hop, 3 hops, 4 hops, 4 hops distance. So they use a k-ordered random walk methodology. Okay. The magnitude of k-ordered proximity between a source user and the item is measured with this quantity, where pu to the power of the k is the probability, transition probability from u to the other node of this walk. And here we can see the objective function, the loss function. As we discussed, there is the factorization model. This is the Bayesian personalized ranking method factorization model. As you can see here, there is I and I prime. Okay, so here we have I, and here we have I prime. In this equation, denotes the observed positive items, whereas I prime denotes the unobserved negative items. Okay, so interaction that never existed, and we randomly sample it to use it for training our network. Also, here we have the uniform distribution by which a non-observed item is sampled from the set of all items for our graph model. And also we have the k-order probability distribution for on observed items sampled from the walk sequence. Okay, so the I prime is about the negative items, and the I is related to the items that really the user has interacted in the past. Yeah. There are interactions that are not present in the graph. So non-existing interactions, non-observed. Okay. And there is also the CK, the decay factor for confidence weighting. So basically, this CK is the distance of the node that we want to reach from the target node. Okay. If this distance is many hops, then it should be attenuated in a way. So we want to put less importance in far distant nodes. Okay, so this method performed 2 experiments with the site you like and MoveLens 1 million dataset for precision recall and mean average precision metrics. Okay, and these are the reported results. They outperform classic methods like Bayesian personalized ranking, the matrix factorization, and other methods. Okay, so the authors of the paper claim that they can capture high-order information. So by using this k-order random walks, they can incorporate into their model higher-order information, not only the adjacent nodes, but nodes that are far from the target node. Now about the third paper, the graph rec. presented in WWW 2019. Again, here we can see that we have social interactions between users and also the user item rating interactions. Here, they want to model the user, but also they want to model to the items. So for modeling the users, they use two perspectives. The first comes from the item space. So we have this equation here. This H is the item space of the latent factor of an item. Okay, as you can see here again, we have the weighted matrix and we have the aggregation function, which aggregates the opinions, the different opinions over an item. Okay, so this is how it works here. So there are different opinions over an item, and we want to aggregate it. And for the social perspective, here we have the social space, latent factor. And again, you have the weighted matrix. This is the sigmoid activation function. And also you have to aggregate the neighbors item vectors. Okay, so in essence, you have a user. And for this user, you go to the neighborhood of these users, the user neighborhood, the neighbors of this user, and you take their ratings and you infer a rating for the target user on the ratings of the neighbor users over the item. Okay. And for the item modeling again, the same idea. So you have to infer the item latent factor. When we discuss about latent factor, is the embedding is like representing a node in a more compact way. This is the latent factor, or else the latent representation of a node. Okay, so when you represent it in a more coherent way, more compact way, this is the latent space. Okay, and here you have again the weighted matrix, the weights of the links in essence, and you have to aggregate over the users the opinions of the users over this item as it is shown here. Okay, so you aggregate the users' ratings for this specific item. And this is the equation. Again, in this graph convolution network. And in the end, we see it in whole now, all the architecture. This is the user modeling part that contains the item aggregation and the social aggregation. And we have also the item modeling part, which contains the user aggregation. So all these three different information is used in order to be concatenated in the end and provide a rating prediction. The prediction for a user over an item. Okay, this is the algorithms architecture. And we have some experiments here in two datasets, Chow and opinions. And they wanted to measure the mean absolute error and the root mean squared error. And they have some baselines also, the probabilistic matrix factorization, the social matrix factorization as baselines. And here we can see the results. The graph rec outperforms the other methods in most of the cases. Okay, here it's not. It's mean absolute error. So the difference should be the minimum is better, okay, in mean absolute error and root RMSE. The smaller is better, so the graph rec outperforms the other methods. So this was like a family of algorithms in the social recommendation, and now we proceed with another family of algorithms which are related to the session-based recommendations. Okay, so in the session-based recommendations, the main idea is that we work with the data of a session, of a user session. Here we can see an example of a user session. Usually the sessions are anonymous. Okay, we may have users who did not log in into our eShop. We just keep track of the session of this, but we can have also users who have logged in and we know their IDs, etc. Okay, so there is a lot of work right now in the cases of predicting the next click of the user, or predicting if the user, what the user is going to click next, because the services need the users to be engaged. And they know that if the user, you lose the attention of the user for 2 seconds, he may leave to another service. That's why it is very important for the recommender systems to engage the attention of the user constantly, continuously. Okay, that's why these session-based recommendations are very important, because it is not its goal is not the long-term preferences of users that are like basketball, for example, but it is about the short-term intention of users, what is going to click next. Okay, so that's why it's very important. Here we can see some works, early efforts, like the SRGNN, AAAI 19, only models each session sequence with directed graph. However, there are very, as you can see, there's a lot of papers here in highly prestigious conference like TAP, SIGIR, Wisdom, CIKM. So it's like a lot of work, as you can see here, with using graph methods. We will see this DGREC from Wisdom. And so here they enrich the relations in graphs with other sessions or additional links. Okay. So let's see about the first one, the CRGNN from Yu et al. In AAAI. So as we said, these sessions are usually anonymous. So they use this graph with the interactions. So as you can see here, these are items, V1, V2, V3, the items that are the user has interacted in the session. From these items, they create a connection matrix by using the outgoing edges and the incoming edges. So this is how they build the information. So they have this graph of the sequence of the items that have been interacted from the user, and they put it in this graph neural network. It's an attention mechanism. Here they build an embedding for every item. Also, they use the local global embeddings of the session. And in the end, they have a softmax layer, and they make a prediction of the item which is going to be clicked next with some probabilities. Okay, these probabilities sum up at 1. This is the softmax loss function. Again, we can see some reported results here. In terms of precision at 20, the number of recommended items, or the mean reciprocal relevance. Okay, the mean reciprocal relevance is related to you have just one item which is interacted, and you have 19 non-observed items in the recommended list, and you just want to see in which rank do you predict the correct one. Okay, this is the mean reciprocal relevance metric. Moreover, the DGREC method, they wanted to bring information from dynamic, from influence by the friends, from the context dependent. So they want to bring information from different contexts. So they have the user, the session, they have the user, they have the time step. Okay, the time step. From time step T, you want to predict the time step T plus 1. So here is the item profile of the user for the first session, the second session. A user may have different sessions during a day in the service, and in each session he may interact with different items. Okay, so in their idea, they want to bring the long-term preference of users. He likes basketball, he likes tennis, but also they want to take under consideration the very late intentions of users. So he saw an article about football, and now about ping pong, etc. Okay, so these are the two things that they want to express in their models. They use a convolution neural network. This convolution neural network co-evolves information for the target user by using the features of the nodes of the adjacent nodes of the target user, okay, as we described it before. But also in their model, they want to take under consideration the short-term and the long-term preferences. That's why they are using also a recurrent neural network. A recurrent neural network has some building blocks of GRUs, LS, long short-term memories, which help them to forget and make more importance, give more importance to more recent information or interaction. Okay, so this is how they employ the recurrent neural network, and in the end, they create different item embeddings. For every item, they have a compact representation, and they use this in order to have a item-item similarity representation here, a softmax again, and in the end, the probability that an item will be clicked next. Okay, so this is here the information that comes from dynamic interest of the users. So the current session information. Okay, an LSTM is also adopted. We have the short-term preferences, the long-term preferences, and we concatenate them by using this concatenation operation here. And here again, we have the weighted matrix, and we have the activation function as ReLU. Okay, here is the concatenation of the S and L. The S is the short, the L is the long preferences. in their model, they have this alpha. What do you think is this alpha? This alpha? This is the graph attention network that we discussed before. So they want to understand what is the node which should be placed more importance. Okay, that's why they have this alpha. And okay, then they have this operation, the weight matrix, the H matrix with the node features, the sigmoid function, activation function, and so on. This is the softmax question that is used for the graph attention mechanism. Okay. And yeah, this is how they aggregate the importances, the features of other nodes. So they ran experiments with Delicious, Duban, and Yelp, and they reported better results in terms of recall and normalized discounted cumulative gain. Okay, so you see here competitive methods, item KNN, Bayesian personalized ranking, recurring neural networks. Okay, so let's see now an example of a graph convolution neural network that exists also in the book. Okay, so in the book, in chapter 8, we have this 8.10 section, and we will see here a step-by-step example of the slides of this example, step-by-step. We start with a graph. This graph is about online publishing house, and we want to make recommendations of articles to the readers of this online website. Okay, so what is the information that we keep? We have these blue nodes are the readers. We have Peter, Nick, and Maria. They have these red interactions, which are the likes. Okay, he likes article 1. Peter likes article 1, likes article 2. We have the green edges, which is the collaboration of these scientists, let's say. And we have also the blue edges, which are the features of the nodes. Okay, so these blue edges is just the node features, as we discussed, which we use this H variable, okay, in the notation. Okay, from this, what we want to do, we want to predict the research interest of Peter, which is in the center. So we want to express this node, the features of this node, and specifically which occupation, the profession, and which is the interest of Peter. Okay. So there are also other features of the nodes. The first, the nature is the title of the journal. Biology is the scientific domain. And okay, as you can see here, based on the 2 articles that he has liked, he should be probably in the machine learning or biology domain. Okay. And we can infer also his interest or occupation by the collaborations with other users like Maria, professors both. Okay. So we use these concentric convolution layers. We have the first convolution layer and the second convolution layer. And we want to implement a convolution network, graph convolution network. Okay. So what do we want to do? we want to aggregate information that comes from neighboring nodes. Okay. We want to forward the information to the next convolution layer, and we want to establish a layer propagation. So we have two types of edges. The green is his collaborations with other scientists, and the red his preferences. And now here we can see our propagation rule. Okay, see, this is the equation that we use to propagate the information. As you can see here, and here they are all defined. We have this H, we said is the latent representation of node I. We have the weighted matrix, the H representation of the target node. Sorry, this is the J node, an adjacent node of the target user. We have also R, which is the R is the type of the link. If it is red or green, red is the preferences of the user, green is the collaborations of the user. Okay, so we have different types of edges. And here, the second big sum is the J is the number of adjacent nodes, is the neighborhood of the user under the link type R. Okay, so this is the equation that will be used to propagate the information. As you can see here, also, we have this, the aggregation that we want to perform. We can use different aggregation functions. We can use the average of the ratings of users to express them, or we can use a concatenation operation. Okay, it depends on what do we want to do. And in this case, we aggregate we use this aggregation function, and then we can decide if it will be, let's say, concatenation or the average of the ratings of the users, of the neighbor users to the target node. Okay. And here we can see the different variables of this equation. Okay. Sigma is the sigmoid activation function. W is the weighted matrix. And as you can see here, the aggregation function may be either the average operator, okay, or a concatenation operator. So in our case, since we have, let's say, attributes, categorical attributes, it's better to make a concatenation operation, I guess, okay, because we don't have really ratings. If it was be like ratings over items, then it could be the average operator would be more preferable. But here we can have them, this concatenation operator suggest. So this is the notation for the concatenation operator. This is these parallel two lines denote the fact that you concatenate two vectors. Okay, the target vector with the adjacent node vector. When you concatenate, in essence, you take the features of one node and concatenate with the features of the other node. Something like this happens. Okay, so in the end, what will be the final predictions? We will now, based on our intuition. Okay, so if we see here, this is the title, and this is the scientific field. Based on the Article 1 and Article 2, Peter's research interest is biology or machine learning. Through the nodes Maria and Nick, the other type of nodes, we may infer the occupation of Peter's, which is the university. Okay, so based on this, we can have our results. And of course, we can express all this with the linear algebra matrices. Okay, so we can have the the inverse of the degree matrix, the adjacency matrix. Here, that gives us, as we discussed, the transition probability matrix. We have the H, which keeps the features of the nodes information, and the W, which is the weighted matrix. Okay, so we can use this linear algebra operation, and we take the sigmoid activation function to propagate the information from one layer to the next layer. Okay, from L to L plus 1 layer. Of course, we can use all the other representations. Instead of the transition probability matrix, we can have other type of information like the Laplacian matrix, okay, which is also very helpful in terms of clustering operations. Okay, so we can also use it to propagate this information. Instead of the transition probability matrix, you can have the Laplacian matrix here. Okay. Okay, now we go to the second Jupyter notebook for GCNs. Again, if you go, we can go now to the website, and in this, let me find it. I have to open it again, I guess. Well, as I told you, for those that arrived in the second session, there will be a webinar which will be on 16 and 17 of November, introducing this book. Okay, the whole it will be 10 hours lectures during this weekend, and one book will be given also, and all the material which is accompanying this book. At the moment, for this tutorial, we will now see the code for this example, the example 8.10 from the book. Okay, it is online in Colab, and here you can see the code. And of course, we have this graph, and we use again this Network X library to represent the nodes and the connections of the nodes. And okay, we have this graph, and then we represent the nodes of the graph, Peter, Nick, and Maria, with vectors. Okay, we have vectors, and as you can see here, we have the concatenation aggregation function. Okay, and we use the objective function here, the sigmoid activation function, and we take the product of the weights and the features of the node. Okay. So in the end, in the very end, we can conclude that Peter is interested in biology and machine learning. Of course, this is available, and you can have a look later on your own. Okay, this code. Is there any question so far? Well, we will continue with node embeddings, and then we will have some material about metapaths and the work in health domain. Well, in network embeddings, what we want is to express a a node in a more compact representation. Okay, so here we have the node, and we want to express it in a more compact way. Okay, in a d-dimensional space. Okay, in a space which has less dimensions. Okay, this is the idea of node-to-vec algorithm. So we have the original network, and we want to represent two nodes of the graph in a more in another space. This is the latent space or the embedding space. Okay, and maybe in this space, these two let's say users come closer, or this could be proteins. They can come closer, or they could be like diseases, or a protein and a disease. Okay, you can use it for these technologies for drug repurposing, for example, as we will see later. This is a way that they have found drugs to apply for the COVID-19. Okay, so they just computed the relevances of nodes of a graph, other dimensional space. Okay, so here we have the dot product of the two vectors of u and v. You take the transpose of the one vector, and you can then compute this similarity. It's very close to the matrix factorization idea. Okay, you take the product of the user latent factor times the item latent factor, and you compute if the user is interested about this item. Okay. And in the end, in the new latent space, you want to see, are they connected? Do they share networks? Do they have similar structural roles? Okay, in order to make these conclusions. Okay, so here we can see some loss functions which use either the square loss pointwise loss function. We have the two embeddings, node embeddings here. Okay, you take the first embedding times the second, here is the transpose, and you want to see how far this computation, this product is from the ground truth. Okay, the ground truth could be, for example, the rating of user U over item V. Okay, so this is the idea here. But also you can express it with, instead of having the user item rating matrix, you can have a matrix of similarities of nodes. You can express it in this way by using the multi-hop similarity measure. Okay, so there are, again here we have algorithms like deep walk, like node-to-vec, and of course, you can apply walk methods in order to infer similarities or distances between nodes in this new dimensional space. Okay, and of course, you can use technologies like the skipogram technology or mechanism where you want to predict which will be the close nodes of the node of the target node. Okay, so if I put a word, what words will be before this word and after this word, around this word. Okay, so this is the skipogram model. And in the end, you can have this information in the two-dimensional space. You can bring, for example, close users with items. Yeah, you can have different representations, or you can have here diseases with proteins, the target of drugs. Okay, so you have, let's say, drugs, and these drugs target specific proteins. You have diseases that also make harm to specific proteins. Okay, so you can have all this in a graph, and you can just make some kind of the application of specific algorithms like random walk with restart, and bring into surface the fact that specific diseases may be cured by specific drugs. Okay, so this is how they found some medications already used for COVID, as we will see in later. Again, here we can see the gut information propagation method used in the heterogeneous graph network. So again, okay, I will have a recorded of the last 20 minutes. Or what? Anyway, so here, here we can see that this is the softmax again loss function, and they want to make note attention to understand the attention to understand what nodes should be considered as more important in this method. Okay, of course, there are some limitations in these works. For example, these random walks are not is like a offline step that you have to consider, and that's why it's not conducted and not. This is a not end-to-end learning process. Okay. So now we proceed with metapaths. There is a lot of work in trying to use these metapaths, which is like these metapaths carry some semantic information. Instead of having and considering all the paths, all different links, someone, an expert, a medical doctor may just be focused in specific type of paths that carry semantic information more important for him, let's say. We will see two methods like MP4EC and NoACF. So in these metapaths, you can have, for example, here, we have a tripartite graph. It consists of users, movies, and attributes, categories of movies, let's say. And here you can have a metapath that says, for example, UMU. UMU is like the collaborative methodology. So it's all the paths that connect to users within a movie. Okay. Someone may also only consider the UMT-MU metapath, which is those users who view the movies having the same type. Okay, so you can just concentrate in specific type of connections and run your algorithms only on these metapaths. Okay, so this could help a lot in your explanations. For example, in the left explanation, because your friends have also this movie. Okay, this is the UM metapath. Or in the right explanation, because you have seen many drama movies, UMGM, user, movie, genre, movie metapath. Okay, so you can use these metapaths for explaining, let's say, your recommendations. There is this work of aspect level deeper collaborative. Okay. We are live.
Yes, I can see you.
Okay. Okay, let's continue. Well, let's say, yeah, for the metapaths, there is a lot of work. We can find this work, and of course, I will make available these slides for you to see them in a comfortable way. Okay, so let's see this work. This MP4EC. This is one work that we did during the period that I was in Dublin, working with UCD, University College Dublin. Okay, a great team there. And we had these meta paths. We had the users, the movies, and the genres of the movies. And we used these meta paths to train some neural networks. We used these meta paths to compute similarity matrices with a different semantic meaning. Every similarity matrix here has a different carries and different semantic meaning. Okay, so we have user movies user, movies user movies, etc. We put them in an MLP, multi-layer perceptron. We have also an attention mechanism. And in the end, we have also explainability, the user item explainability matrix, because we use these metapaths, so we can explain our recommendations. And we have a loss function here, random prediction loss function. Okay, so this is the algorithms architecture. Of course, there is a lot of theory in how you implement this explainability user item matrix. Okay, so you need to express how explainable an item is for a user and keep this information in a matrix. And of course, in this paper, we had this trade-off between the mean explainability precision and the accuracy of our model. Okay, so there is this trade-off in our experiments. Of course, here we can see an example of how we can recommend a movie to a user by using these metapaths. For example, here, this metapath, movie user movie, shows that other 49 users have co-rated this movie for you, with you. Okay, and you have also two genres in common. This Alien movie with the Star Wars movie that you have interacted in the past. Okay, so you have a lot of explainability power in your recommendations by using these metapaths. Of course, these metapaths in medicine, they are called like pathways. Okay, so they call them pathways. Of course, also there is these knowledge graphs. The knowledge graphs here, usually they have triplets of information. Okay, the triplets is the head entity, the relation, and then the tail entity. Okay, head entity, relation. When you build a knowledge graph, you usually have triplets of information. So you have a user which interacts with an item. You have an item that has this attribute. So all information is inserted into the knowledge graph as triplets. Okay, and of course you can run methods like reinforcement learning methods. In this work, they use a reinforcement learning method, and of course it is very popular. This deep reinforcement learning with DeepMind and all these algorithms like DQN, A2C, etc. Okay, here you can see the policy, which is a dependent probability. If I am in this state and this is my action space, what is the probability to do this action? Okay, so this is how they use it in this knowledge graph. They had this reinforcement learning method, and they have also the rewards. And they, in essence, they have a reinforcement learning implemented with neural nets. Okay, so here you can see fully connected layers, activation functions. You have the value of the state, the current state, all these materials that building a reinforcement learning algorithm. And of course, this is implemented in a knowledge graph. Okay, and we see here some experimental results. For the last 10 minutes now, I will show you some last slides in the field of medicine that can be applied for algorithms from our field, which can be applied in the domain of medicine. Here is another work about multimodal knowledge graphs for recommended systems. In this work, the authors incorporate into their models not only user item information or textual information, they take photographs. Okay, they put into their network and use the, as we said, the convolution neural nets. Okay, here there is the ResNet. They use the images themselves as input in their model. Okay, so it's more advanced. That's why they call it multimodal, because they use, except of textual information, also image information, and a lot of other structural information objects. Here you can see again the attention layer. We have discussed a lot about this. In the end, what they aggregate is this function, where, as you can see here, this E triplet is the embedding of its triplet, the head, the relation, and the tail, and P is the attention score of the triplet. Okay, and this is the attention score in the end. Okay, so this is how they incorporate and they convolve their information in this graph convolution network that they use in this knowledge graph. This is the overall systems architecture. And of course, we see some experiments and an ablation study. So they beat the K-GAT, the knowledge graph attention algorithm. This is the multimodal K-GAT. And they have found that this image visual modality plays a very important role in their experiments. Okay, so this is one finding from this work. And now the last part, which is the thing that I work in the last 5 years, the medical knowledge graphs. As you can see here, we have graphs. Instead of having users, items, genres, movie genres, etc., we work with this kind of things. We have from biology, we have the DNA, we have the RNA, we have the proteins. This is the protein-protein interaction networks. Okay, we have the drugs, which target specific proteins or enzymes. And we have also the diseases which harm specific proteins or genes, etc. And all these things are like a heterogeneous knowledge graph with many different type of networks, graphs. Okay. Of course, we have done some work on this. There are many questions to be answered. Here we can see an example of drug patient procedures, interventions, or diseases that you can use in your algorithms. So we discuss about graph-based algorithms applied in medical data now. Okay. And you can find similarity search in graphs, okay, to find, for example, diseases that are related or proteins that are related. Of course, you can use again metapaths. Okay, you have the patient, you have the treatment plans, you have the drugs used in these treatment plans. So you can make a lot of, let's say, you can apply algorithms to find frequent metapaths to connect patients with other patients, diseases with other diseases, etc. For example, here we can have question, which drug should we recommend for patients? And have drug recommendations based on specific metapaths that you can have. We have some work here. You can download some code from GitHub. And as you can see here, in these knowledge graphs, medical knowledge graphs, you can have proteins, you can have different type of edges, gene regulation, signaling, one cell with another, how it communicates. All this stuff is a huge amount of information inserted in protein-protein interaction networks, metabolic networks, genetic interaction networks, gene regulatory networks, cell signal networks. And I don't know if you know, but that the Nobel for physics was given to people from information domain, okay, from our domain, I guess. And this is because we are capable of dealing with this huge amount of information, okay? And okay, this is like a good way to a good domain to work with. So here they have this drug repurposing, which for us could be like drug recommendation. And what does this mean? Okay, so there are already existing drugs, and they want to see if these already existing drugs can be used for new diseases like COVID-19. Okay, and let me give you an example of how this has been done already. And I see a lot of, let's say, similarities with our own work. So here we have this paper, the drug repurposing for COVID-19 paper. And what they did, they used all this information. That's the information that I showed to you. So what is this? This molecular profile, the chemical structure of drugs, the adverse profile of drugs, the molecular docking, the electronic health records of patients, the pathway analysis, genome profile, the network proximity. All this information is graphs. Okay, and here you can see they have the input data like the proteins, the protein-protein interactions. They have the proteins that this COVID targets, harms. They have also the drugs and the targets that of these drugs, which are the proteins or enzymes, etc. So they have all this information. And what they did, they have they try to make, let's say, network proximity, the thing that we discussed. Okay, if something is similar to something else, if a drug is close in this embedding space to a protein. Okay, so the network diffusion with random walks and all this stuff. In the end, what did they do? They have a list, a ranked list of drugs. They, in essence, they created 11 ranked list of drugs. And they use specific methods like union, average rank, border, and for ranking aggregation. Okay, so they have 11 different ranking lists, and they just want to aggregate them in the end to understand if there will be drugs which could be used for the COVID-19 disease. And in the end, as you can see here, chloroquine was one of the selected that they have in this at least paper was found as one drug that can be used for treating the COVID-19. Of course, there is a lot of stuff which can be found there. And in the end, as you can see, in this embedding space of COVID-19, they have these drugs, they have the diseases, and we have, let's say, the drugs which could be used for this disease. And you can see that this chloroquine is very close to the disease of COVID-19, etc. So these are things that can be applied also to other domains, and specifically to the medical domain. So biomedical engineer could be also a choice. For our case, we have also a service for COVID patients in this DrugRec website that you can check it out, and there are also explanations about the drugs which can be used for treatment. So check our DrugRec service. It's only and now the last Jupyter notebook. I think, yeah. This is like a notebook related to drug recommendations using metapaths. So the code is available also in GitHub, and you can have access on this. So we start with this simple network with patients, drugs, and treatment plans. And in the end, we use these metapaths in order to find the most frequent metapaths and recommend user to the patient some kind of drugs based on similarities that we have seen in the graph. Okay, so I think it will take some time for us to run, but you can find it also later. So let's give it a try. In the meanwhile, you can, since I have finished this tutorial, you can ask me anything you want about graphs and or my book or whatever you want. Thank you very much for being here. It was a pleasure. Slides. Of course you will get the slides. This is a promo for me. I will make sure that you will get all this stuff, but you will give me some days. And if you follow me in LinkedIn, for example, okay, you will, yeah, I will probably release them. Okay. Yeah. Any other question? Yes. Well, about the book, as I told you, it's a follow-up webinar, which will be in the next month. And as soon as you will participate in this webinar, you will get the book. No, it's not. We don't sell it right now. This version will be given to you for those that will participate in this webinar, which will be in the next month, the Saturday 16th and Sunday 17th of November. And you will get all the materials, which means that you will get the PowerPoints of the book. You will get access to all Python codes of the book, and also the whole book as a PDF. Okay, so I would be glad to continue and see you in this webinar. And yeah. Any other question about graphs? Any hard question about graphs? Yeah. Make me. Yeah.
Also about strategy.
Well, this is like a very ad hoc process, I guess. You have to work with different type of data. And of course, we discussed about attention mechanism. You have to understand what should be the importance of this data. Should you put more emphasis in the user item interactions, or should you put emphasis in the images information? Or so, I mean, you have to work with the data, understand the information that they can bring into your model. But right now with ChatGPT, it's more than profound that you can get more accuracy by using information such as the images that are used from the items of movies, for example. You can get a lot of better performance in terms of efficacy when you use additional information. Yeah, definitely. Yeah. Any other question? Is there any question from the online? Yeah, I think there are 20 people there. Eh? 50? 15, okay. Yes? What embeddings? The size, okay, yeah. It's very important, definitely. I mean, what you mean an embedding of 128 the size, or 256 or 512. I guess you need a lot of storage in order to work with all these things. And of course, there should be considered other methods for dealing with this, like LS locality sensing hashing and all this stuff. So it is definitely a thing of problem to deal with. If you are Google, then you will have algorithms that use this locality sensitive hashing in order to represent the information and put it index it into your database. And of course, all this are required to have a lot of storage and use with the high dimensional embeddings. So
we can say that higher dimension is better.
Well, no, there is a limit, of course, and yeah, that's why when we train a network, we may choose, for example, a layer to be, let's say, with 64 nodes. Another could be like with 128 nodes, etc. So it depends on. We have to make a grid search on the size of the network and the layers. Yeah, definitely. Yes.
Is a question.
Yeah.
Are there any areas of research and serendipity?
Serendipity. Okay, so serendipity has to do with diversity and with novelty, and right now I do not remember some works about having this graph neural networks. I presented to you many works that have explainable recommendations. Okay. Yeah, there should be works about diversity and novelty of recommendations. And in this case, there is also a trade-off between the effectiveness of the algorithm and the novelty of or serendipity of the recommendations. So if you want to be novel in your recommendations, you will have a cost of losing in terms of accuracy. Okay, so you have to find out the connection between these two curves. Okay, so that you have both effective and diversified recommendations. Yeah. Sequential. Yeah, I showed you this works about session-based recommendations. Session-based recommendations is sequential recommendations. The only thing that differs is that you don't have just a sequence, but you have a session which is more better defined. Okay, in the sequence recommendations, you just have the next item, which the user has interacted with. Okay, so the methods that I showed you about session-based recommendations is, let's say, subcategory of the sequential recommendations. Okay, of course, in these sequential recommendations, you need to, for evaluating these sequential recommendations, you need a different evaluation protocol. You should not use this, let's say, split that you do with four-fold cross validation, but you need to change your evaluation model by using this frequential evaluation. So you use some data, you predict the next item in the sequence, and then you insert this item in the training data and you predict the next. So it's like a frequential evaluation that should be used in this sequential recommendation or session-based recommendations. Okay, I think that now we have met and we have also time to discuss offline. If there is no other question online, then I think we can close this session. Thank you for your presence here, and we discuss in the later. Okay.